Okay, so let's talk about stacks and queues. They're very commonly used data structures in computer science. When you're trying to solve a problem, which is sometimes very difficult to think about in terms of arrays or any other kinds of data structures, sometimes stacks or queues make it easier to deal with coming up with a solution. A typical example would be that suppose you're going through sort of a maze and you want to backtrack and you like to remember the path, and stack seems to be a great way to do that. So we'll talk about some of the stack operations and queue operations. So you can think of a queue as sort of like a data structure where you can use to implement a router. So you have some sort of a first in, first out type of a service, a queue in a grocery store, for example. So they are very important data structures, and they restrict the uses from too few operations. In case of stacks, you can only pop and push into a stack, and in case of a queue, you can only enqueue and dequeue from a queue. So let's take a look at some of the things that we need to understand in terms of these abstractions. So we're going to start with the queue abstraction. So the queue abstraction is essentially that you do have a queue of items where you can add something to the back of the queue. So you will add from here, and then you will remove from here, from the front. So that's the whole idea. And you can think of lots of different applications that deals with some things like that, where you have to really deal with a data structure or a situation where you're adding something to the back of a queue and removing something from the front of the queue, which is, we are very used to this kind of concept. And lots of applications require this sort of data structure to implement them. So you add from the back and you remove from the front. That's the idea. Now, in terms of implementation using some sort of a linked list structure, we can say that we're going to use a linked list structure to implement a queue. But in order to identify the front and the back, we're going to be keeping 2 pointers. So front is a list pointer to the first node of the data structure, the list data structure, and the back is another pointer to the back of the data structure, back of the list data structure, which is the dummy node here. So essentially, if you like to add a new node to the queue, you're adding to the back of the queue. Now, as we saw in terms of adding to the end of a linked list, the ideal thing to do is to create a new node and make that the dummy node by making this going to null, and then change the data here to the new data you want to add and make this pointer go there. And that's what this picture shows us, that you can make you can add a new node to the end, make that the dummy node, and make the old back node or the dummy node become the new node. So in terms of writing code to understand this, what you're really doing is, first of all, you're creating a node. So we can create a node with the type of code you were looking at already. So let's say list L is alloc struct list node. So let's take a situation like this. So this is really the L we are talking about. And then we like to make sure that the L arrow next is assigned null. So let's make sure that's the case. And then we want to make sure that we take the old back pointer and then make the back arrow data to be the new element that we are trying to add to the end of the queue. And then we take the back arrow next, which is this pointer here. We're going to make that go to the new node. Now, one other thing we need to do is to make sure that we call the back is going to be the new node reference L. So without any annotations, this is sort of the piece of code that you write. You create a node, you make the correct pointers, and you have a valid linked list. You can in fact check whether the front to back is a queue or not. So that's one of the contracts you can write. So that's adding an element to a queue. Now when you try to remove an element from a queue, what you do is you remove the front of the queue, the front element of the queue. So what that means is you take this pointer and make it go here. Now keep in mind that the address is, front is an address, it's a pointer. And so this node is really called front, or the address of that, that's the address of that node. Now this node is called front arrow next, because if you have, if you know the next point of front, which really contains the address of the second node. If you want to think about this, this is really the front arrow next, arrow next. So what we need to do is to remove this node. We have to just change the front pointer. So we can change the front pointer by saying this. Front is assigned front arrow next. So all it does is to move the front pointer from the old front to the new front. And we do not have to worry about this node because cnode garbage collector will take care of, will remove the old front. Now this is not the case for C, but in cnode this is the case. So so we can assume that the garbage collector will remove the front node. So that's the dequeue operation using. Now let's talk about the stack abstraction. What is a stack? Stack has two restricted operations. One is called the push operation, which is essentially pushing something into the stack from the top of the stack. So if you assume this is the top of the stack, you're pushing this new element. So here's our new element or new node to the top of the stack. And now pop operation means you take the top of the stack and you pop it out and you take it out, so the stack gets reduced by size 1. Now one thing we need to make sure to understand is that the last element that was pushed is the first to be popped. So we call it last in first out sort of thing. This is the structure where a stack is a last in first out structure. Now this has a lot of applications, like for example if you're navigating through a maze and you're going through some nodes here in a maze. So let's say that you were at node A, node B, node C, node D. As you go through the maze, you're going to be pushing your nodes that you were in into a stack. So you can push A into a stack, B into a stack, C into a stack, and then D into a stack. At this point, if you come to a dead end, for example, and then you can always backtrack and see where you were before coming to D. And so that allows you to backtrack in the reverse order. So stack is a great data structure for sort of, you know, finding, backtracking or reversing something. So that's a good way to use a stack. So the main operations in a stack interface are the push and the pop. So in this case we are saying let's push something, an element into the stack S, or we can pop something from the stack and it will return an element. And in terms of implementation, what we're going to do is we will talk about some of that in the actual code. So here we are going to talk about how we write the code to implement the stacks using list. So let's start with the definition of a stack. We define a stack as a pointer to a struct stack header, where the stack header contains a bunch of fields. We have a top, which is pointing to the top of the stack. Since it's implemented using list, it is a list pointer. And also the bottom of the stack, that's also a list. Now keep in mind that we don't really need to have a bottom reference to the stack, but it makes sense to have a bottom reference so that we can make sure that there's a segment from top to the bottom. And then we also have the size of the stack, which is going to come handy when we write functions. So most of the standard functions are implemented here, checking whether something is a stack or stack is empty, or returning the size of the stack and so on. Now, so what we will start with is to start developing the functions for creating a new stack. So creating a new stack means that first of all you have to create memory for new stack structure. So let's just say that stack S is going to be alloc struct stack header. Now, as you know, the stack header is really one that contains three fields: the top of the stack, the bottom of the stack, and also the size. Now, since we are implementing stacks using linked list, we have to also create a list node, which will become the dummy node for the moment, because this is the beginning of this creation. And so we create a alloc memory, enough memory for list node here. Alright, so now we did that, and so the next thing we need to do is to take the top element. Perhaps before we do that, we're going to assert that S is not equal to null. So in case the memory was not allocated, S could be null, but so you want to make sure before you dereference the S is not null. So S arrow top is going to be this dummy node, and S arrow bottom is also going to be that dummy node L, as well as S arrow size would be equal to 0, and at the end of this we can just return S. So this is the stack new code, and what we want to do is to make sure that first of all we want to make sure that the stack you're returning is a stack. So we're going to say is stack, and the result is a stack. And also we want to say that the stack is empty to make sure that there's nothing in the stack. We just created it, so we will make sure that the stack is empty. So those are the two contracts we write to make sure that we are doing this correctly. Now the push operation. So how do we push something into a stack? Now to push something into a stack, we have to create a new node. So first of all, let's create a new node. So alloc struct list node. So let's create a new node, and then we are going to initialize the data inside that node to the data that was passed to us, which is called E. And then what we like to do is to make this the first node in the list, because when you're pushing something to the list, we're always adding to the top of the list. And we define the top of the list to be the first pointer in the list, top of the stack to be the first pointer in the list. So what we're going to do is we're going to say L arrow next should point to the S arrow top. This is the old S arrow top. And then we're going to say S arrow top should be pointing to this new node L. And we also need to increment the size. S arrow size would be incremented by 1. So the stack push would be an operation like this. And there are a few things we require. Like, for example, we want to make sure that you will have a stack and you can push something into that stack. And it also ensures that once you put something into the stack, it's still a stack. The stack did not change, it's still a stack. So this is the stack push. Let's talk about the stack pop. Now stack pop is, again, we want to make sure that it is a stack so we can pop something, and also we want to make sure that it's not empty. So the stack is not empty. Now we want to ensure that after you pop something, it's still a stack. Alright, so how do we pop something out? So popping means that removing the top element. Alright, so we want to remove the top element. Now we can have an assertion here to say assert that the stack is not empty. Now this kind of assertion is helpful even if you don't check with the annotation flags, the -d flag. This assertion will be tested to make sure that before you dereference something, you will be making sure that that point is not empty. And so what we're going to do is we're going to take the S arrow top, and then we're going to take the data field of that because we need to return an element back to the calling program. So we'll have to return this element. Let's save the element first by taking the S arrow top arrow data, which is going to be the data field of the first node in the list. And then what we want to do is to make the S arrow top, which is now pointing to the first node in the list, to point to the second node in the list. This is how you typically delete the first node of a list. So we're going to say S arrow top is going to be S arrow top arrow next, and so that will delete the node. And because C node has a garbage collector, the first node will be recovered and given back to the heap, and so we don't have to worry about that. And then we have S arrow size would be decremented by 1, and then at the end we're going to return the element E. So now we develop these pop and push functions and the other functions that we require, and so we have this all this in a function called stacks.cnode. So let's save it, and we can make sure that by using coin, this is going to be there's a parameter missing type, so this means that the coin requires obviously elim.cnode as well as list.cnode and stacks.cnode. Okay, so if we provide all the things that we need, the coin will make sure that we have all the functions working fine. We don't know that. We will test that. We could test that independent of the stack thing. So, but in order to test it, what I will do is to write a function called stack tester, and so try to test this function. So here the goal is to write a stack print function, but the problem with the stack print function is going to be that when I print a stack, the only interface I have to the stack is the stack pop. So if I pop elements from the stack is going to be empty. And since I don't want to do that, what I'm going to do is to save the size of the stack in an array, or save the elements of the stack in an array in the reverse order, and then I will put it back into the stack. I'll push them back into the stack so that the order will be retained. So the goal is here that the stack print should retain the order and also return a temp back to the main program. So anything that mutates the stack needs to be recovered at the time you print. So here, if you push something into the stack like me, push something into the stack like Guna, then you print it, then you should see Guna first and me second. So let's take a look at this. See if we can run this thing. So we were going to compile this with ccnode stacks and the stack tester. Okay, make sure everything is okay. Well, we have a problem here. So in this segment of the video, we're going to talk about how to test the stack library we developed using coin. So I'm going to start with the coin by loading the coin. So this is the command you want to give coin. The functions that the files you want to load are the elim.cnode, list.cnode, and stacks.cnode. And the elim contains the type def for the elim, which is a string for this particular test run. So let's load the file, and then the first thing we're going to do is we're going to create a new stack using stack new. That creates a new stack. Now notice that there's an address given that tells you exactly where the stack is, and it seems like the address has 4 bytes of memory there. It's an address with 8 hexadecimal digits. So it's really a type of this. S is a stack header pointer, which is as expected. S is supposed to be a pointer to a stack header. So let's try to push something into the stack. So we're going to say stack push into the stack some string. So it does it something. So we can test that in a little bit. So let's push another one into the stack. So it pushes something into the stack. Now let's try to pop something from the stack. So if you pop something from the stack, so say stack pop S, this will return an element which is supposed to be guna, because guna is the last one that was pushed. So if you pop, it will return guna, which is a string. So let's do another stack push into the stack horse, and let's do another push into the stack push S dog, and then let's do now we have a few things in the stack. We have me, horse, and dog. So if I pop first, let's do a pop first. Let's do a pop from the stack. So if you pop it, then you're going to get dog, and if you pop it again, if you try to pop it again, you should get the horse. If you try to pop it again, you will get me. Now the stack is empty, so we can test whether the stack is empty, which is true. And then if I try to pop again, and the assertion failed because we couldn't pop from the stack. So that's a simple test of stack functions. In this segment of the video, we're going to talk about how we can implement queues using linked list. So as before, we have a queue header, which is a struct. Then we have a pointer to the queue header, which is called a queue. So a queue is really an address. It's a pointer to one of the structs queue header. Now the queue header contains 3 fields: front, back, and the size. And also isQueue is implemented to make sure that the front and the back are pointing to null in the beginning, and there's a segment from front to the back. Now queueEmpty means that the front and back are pointing to the same thing. And now we will start with creating a new queue. Now creating a new queue means that we have to start with a new queue pointer first. So let's just create a queue. Queue is going to be alloc. So we allocate memory for a queue header. So allocate memory for a queue header, which will give us the memory for the queue header node. Now the queue header node contains the 3 fields: list, and the int. So we allocate memory for the queue header, and then now since we need a dummy node to get started with, we're going to allocate memory for a dummy node. So it's going to be alloc struct list node. So we allocate memory for a dummy node. Now we have to make sure the front and the back of the queue are pointing to this dummy node. And queue arrow back is also pointing to the dummy node. And then at the end we can return the queue back. So return queue. Now let's think about it this a little bit. I think there's nothing else to do here other than to just return, and we want to make sure that when we return that the queue, we have a valid queue. So we want to make sure that the result that you're returning is a valid queue. And so that's one of the annotations. And also we want to make sure that the queue you're returning is empty. There's nothing in there. That means the top equals to the front equals to the back. So queueEmpty must be true. So that takes care of queue new. So it returns the queue back to the main program. So now the enqueuing means that you're adding to the back of the queue. So that's the goal of enqueue operation. Now, in order to perform NQ, let's think about some of the preconditions. The preconditions are that you must have a queue to begin with. So we'll test to make sure that we have a queue. And after you NQ something into the queue, we want to ensure that we still have a queue. So we call this queue function. And then to NQ something into the queue, what we're trying to do is to NQ a node with the elim. So first of all, we have to create a list node. So we will call alloc struct list node. So this is going to be the node that we will use as the dummy node, in fact. So we will keep that as the new dummy node. So we'll take the current back pointer, which is the node, and then we will set the data, which is currently a dummy node, to this element E. And then we will take the current back pointer, which is the current dummy, and then set that next pointer of that to go to L, which is the new node that we have. And then we want to make sure that we're going to update the back pointer. So Q arrow back would be assigned the node L. So this is the new node here. So then at the end, we want to return from this function, and there's nothing else to do, and Q arrow back is now pointing to this dummy node. We didn't do anything with the dummy node because dummy node is just there to make sure that Q back is pointing to the dummy node, and we have a valid segment from front to the back. You can even test to make sure that you can assert that there's a segment from. So let's do that assertion here. We can assert that is segment So if you take Q front to Q back, so these are two pointers, we can make sure that this is a segment to make sure that we have linked them correctly. So that's our NQ function. And so DQ function is, we want to make sure that one precondition would be that we have a queue to begin with. And then we also require that the queue to be non-empty. So we call this queue empty. Queue empty. So make sure queue is not empty. And also that we ensure that when we return, we have a queue again. Okay, so how do we dequeue something? Dequeue something means that we just have to move the front pointer forward. So we can do another assertion here to make sure that the queue is not empty. So in case we don't test with the D flag, this assertion will always be tested. And before you dequeue something, the element, the node, we have to save the element in a variable called E. So we'll take the front pointer and then take the data field, which contains the element, and we will be saved. And then we will take Q arrow front. So we have to move the front pointer forward. So we take the new Q arrow front is going to be the Q arrow front arrow next. And then at the end, we're going to return E. So we're going to be returning the element back to the main program, the calling program. So we have this dequeue function developed. And now we can go back and test this with our coin. So let's save this, and then let's try to load this one. So we're going to say cc note, and first we have to load the elim.c note, and then list.c note, and then queues.c note. Well, the compilation failed because I could not, in fact, compile without a main program, so I'm going to use the coin as I said before. So let's coin that. And there's an invalid annotation in line 62 of the queue. So let's go to queues, and look at line 62. Line 62. Okay, well, the invalid annotation is perhaps I left some garbage character there. So let's go back and do the coin again. So this time it seems to be working okay. So I will do q equals q new. So let's create a new queue. So it gives you the address of this new queue. And then what I'm going to do is I'm going to say q nq. So take the queue and nq me into the queue. And then let's take the queue and nq another element into the queue. And then finally, let's do let's test whether the queue is empty. Should be false since we have two elements. Now let's dequeue something from the queue. So when you dequeue, it returns an element. So this should allow us to see what the element is. So notice that unlike the stack, the me is the first one that came out. And if you take q dequeue again, this time I should get guna. And then if you test whether the queue is empty at this point, you would expect this to be empty, and it is true. So this concludes the development of the queue code.